So you have seen that uncharged or neutral objects are attracted to charged objects. And based on the model of positive and negative charges being attracted to each other and positive charges being repelled from positive charges, say, that may seem a little bit mysterious. Why is it that neutral objects are attracted to charged ones? Okay. And so you saw a demonstration with a pith ball, and the idea here is that we have a conductor like so, and we bring a charged object nearby. Okay, so I don't know specifically what the charge is for the charged object. Let's say that the charge is negative. So I'll just draw a bunch of minus signs on this charged object. And if we think of this conductor as having a bunch of positive and negative charges, then the positive and negative charges are free to move on a conductor. And so for positive charges, what we expect to see is that the positive charges are attracted to the negatively charged object. And so they should want to move closer. So we'll get these positive charges that will build up on the side closest to the negatively charged object. And negative charges are going to want to be repelled, so they're going to move as far away as they can get from the negatively charged object, like this. Okay, so the conductor is neutral. There's still an equal number of positive and negative charges. Here I've drawn 4 of each. So you would, I think, naively expect then that you still would have no net force on the conductor because the positive charges are attracted and the negative charges are repelled. So let's draw a free body diagram for the pith ball. Okay, so for the positive charges, there's going to be a force to the right. So that's a force on the positive charges to the right. But the force on the negative charges, which is going to be to the left, is actually going to be smaller. And the reason it's smaller is because the negative charges are a little bit further from the charged object. So we know that the force between charged objects depends on distance. The closer the objects are together, the stronger the force. And so in this case, there actually is a net force to the right, even though there's no net charge on the conductor. And so that's why we see that neutral conductors are attracted to charged objects. But that may still seem a little bit mysterious in terms of, for example, why the paper was attracted to charged objects in the lab. Okay, so this type of diagram where we show some specific locations of charges as pluses and minuses is called a charge diagram. And these can be really helpful for trying to understand what the distribution of charge looks like in certain electrical devices or in some situations that otherwise seem a little weird, like the pith ball. So some things that you want to be careful of when drawing a charge diagram is you'll want to count your charges. A thing that can happen is because minuses are easier to draw than pluses, you might just try to draw lots of each and end up drawing like 5 pluses and 30 minuses because minuses are so easy to draw. So you really want to make sure that if the total amount of charge is supposed to be 0, that you have an equal number of pluses and minuses. So my advice would be don't draw too many charges. You want to draw just enough to represent what's going on. Also, we know that a charged object, in fact, even if it is, say, positively charged, still has lots of positive and negative charges. So we typically only want to draw excess charges, which means the ones that are not canceled out. If you tried to say, well, okay, but like there's some positive charges on the right hand side of this pith ball, but there are also lots of negative charges and lots of positive charges, it would mostly just be a really confusing diagram. So we only draw the excess charges and not the background ones that are canceled out. Okay, and the locations that you draw them obviously matter. Okay, so the whole point in this case, for example, is that the positive charges end up on the right and the negative charges end up on the left. So when you draw these, try to think about whether they're going to be on surfaces, if they'll be spread throughout, and so on. So those are the sorts of things that you want to look for when you're drawing a charge diagram. Okay. So again, this I think explains what's going on in a conductor, but what about an insulator? So let's consider that case. All right, so to understand what's going on in an insulator, it helps to have a microscopic model for what is going on inside the insulator. So if you think of an insulator as being built up of positive and negative charges, let me be consistent with my diagram before. So I had green for positive. Well, atoms have positively charged nuclei. So in an insulator, we're going to have a bunch of nuclei that are positively charged, like this. And there are going to be electrons that are attached to each of those nuclei. All right, so let's say that I have, again, a negatively charged object over here. Well, what will happen to the electrons that are around each of these atoms is those electrons are going to be repelled away from that negatively charged object. So instead of making nice little circular orbits, they're going to tend to want to be a little more on the side that's far away from the charged object. Okay, and what happens then, if you are considering the overall behavior of that insulator, is that the closest side is going to be slightly positively charged because there are less electrons on that surface nearby. And the farthest side is going to be slightly negatively charged because there are slightly more electrons and slightly fewer nuclei in that region. Okay, so the same basic phenomenon still happens. We have positive charges being a little closer to the negatively charged object, and the negative charges a little further away, so we still see a net force. How is that different than what's going on microscopically inside a conductor? Well, in a conductor, there are still atoms, and they're still built up out of nuclei and electrons. So if I draw the nuclei, those are going to look largely the same in the conductor. They're still going to be positively charged and arranged in some way. But our model for a conductor does not have all of the electrons stuck to the atoms. Some of them are still going to be, but each atom is going to contribute some number of electrons to what we think of as a sea of electrons or a cloud of electrons that all of the atoms share. Okay, so the electrons are going to be kind of spread out in some largely random way throughout this sea of electrons. All right, so that sea of electrons explains why the charges are able to move freely. If I put a negatively charged object somewhere in the vicinity here, then those electrons are going to repel as far away from that negatively charged object as possible. And if I put a positively charged object, they'll move as close as they can. And so nuclei tend not to move because they're stuck in sort of what we call a lattice. And that may be either just a chemical structure that they're in, or even just the fact that they're really heavy and hard to move relative to the electrons, which are very light and can jump from atom to atom really easily. Okay, so in both conductors and insulators, we still get this polarization effect, which is the name of this phenomenon that we see here, where the neutral objects, polarization. are attracted to charged objects because they polarize. The positive charges move one way, negative charges move the other way, and the object then has a net force, even though it's overall charge neutral. Okay, and we see that in the case of insulators because the electron clouds get distorted. We see it in the case of conductors because the shared electron sea or electron gas is able to move electrons wherever is necessary. Okay, so in both cases, even though it's the electrons that are really changing their positions, we still will often talk about positive charges moving around, positive charges being attracted or repelled. It's really only in a small number of cases where we can even tell any physical difference, whether it's positive or negative charges moving. Usually, it doesn't really matter whether we think about electrons moving or whether we think about positive charges moving.